So today, folks, we're just going to start by revisiting the NV minus sensor. And then we'll go on to begin our little math boot camp. So just to wrap up our conversation on NV minus sensors, I wanted to remind y'all of the electronic structure of the NV center. So we have our valence and conduction bands of diamond, very wide band gap, 5.5 electron volts. That's why they're transparent. They don't absorb visible light. But then we have this mid-gap set of electronic states. So we have a ground state that has a triplet A2 electron configuration, and we have an excited state that has a triplet E electron configuration. And what we can do is we can use green light, so basically the light from a green laser pointer, and we can populate the excited state from the ground state. What's interesting about this is that there's then multiple ways for our excited state to relax. So we can, through radiative recombination and mostly emission through the zero phonon line and associated vibrational sidebands, we can get red emission, so that's sort of recombination back across the band gap, or back across the defect gap. So this is our red emission. It has a wavelength of about 638 or so nanometers. And that radiative lifetime is about 20 nanoseconds. So that's one channel for relaxation. And that mainly takes you between the little m sub s equals plus minus 1 levels. The alternative mechanism of relaxation is an intersystem crossing. So we can go from E, which is a triplet state, over to this singlet state via intersystem crossing. So intersystem crossing is moving from a state of one spin multiplicity to a state of another spin multiplicity. This intersystem crossing happens most probably from the little m sub s equals plus minus 1 branch of the excited state. And so, and that happens with a pretty high probability. So we end up populating this little m sub s equals 0 singlet state. That singlet state has a relatively long lifetime. Its lifetime is about 250 nanoseconds. And when it relaxes back down to the ground state, it populates this little m sub s equals 0 level. So that's how we initialize our qubit. Is we pump optically, and then we get intersystem crossing and relaxation back down to that little m sub s equals 0 state. And so this manifold is kind of how our qubit will work if we're looking at our quantum information applications, and it's also sort of the energy levels out of which, the electronic states out of which our sensing also happens. So once we have our little m sub s equals 0 state initialized, we can use a microwave to populate the little m sub s equals plus minus 1 states. So microwave pumping at 2.87 megahertz. No, gigahertz. I was like, that doesn't make any sense. Gigahertz populates, takes you from the little m sub s equals 0 to little m sub s equals plus minus 1. So the one thing to note is that when we get relaxation from that singlet state, the long-lived singlet state, to the little m sub s equals 0 state, that results in a decrease in our red emission that we would have normally gotten, because we've channeled some of our excited state through that non-visible radiative channel. And so when we look at an experiment called optically detected magnetic resonance, that's this ODMR experiment, what we end up seeing is a dip in the luminescence intensity. And that dip in the luminescence intensity happens at that 2.87 gigahertz that's associated with the splitting between the little m sub s equals 0 and little m sub s equals plus minus 1 states. And so that's in zero magnetic field. Once you start applying a magnetic field, your little m sub s equals plus minus 1 states split. And that splitting of those two states, that's the Zeeman splitting, it's dependent on the size of the magnetic field. And you can then use the, this equation 2 gamma B. So B here is your magnetic field, so you can use that to extract your magnetic field term, and that's how you get use the NV center as a sensor in the most simple scenario. The other plots here, this is the just normal luminescence spectrum showing that red luminescence at about 638 nanometers. And then this is the time-resolved photoluminescence showing that fast radiative decay and then the long-lived part of the rest of the excited state manifold. Yeah, so you're maybe trying to sense a small magnetic field that's being put off by a paramagnet in your near your sample, for example. NV minus centers are great for both of these types of applications. The fact that it can be initialized optically with just green light makes it very easy to apply as a sensor in many different applications. And this is just an example of magnetic field sensing. It can also sense many other things like electric fields and chemical environments in various ways. But this kind of initialization and ability to move between the little m sub s equals 0 and plus minus 1 states, so those are the two levels of your qubit in quantum computing as well. So yeah, it's great for both. It's much easier to use as a sensor. It's much less, in sensing, we don't entangle qubits. So one little quantum processor by itself is sufficient. And so we don't need to worry about how modalities of interacting these things or of isolating these things from each other, that complication is not something that needs to be taken into account. So it's just a much simpler, and it's much simpler modality of quantum information processing, and that's why it's here already. That's why it's not like a future term application. Okay, so the rest of today's lecture is going to be kind of the start of our math bootcamp. So my initial question is, how many folks in the room are very comfortable working with complex numbers and like matrix algebra? Most of you. Okay, so this might be a lot of review, and so you guys should feel free to let me know if that's the case. I think it's okay to all get on the same page because the intention of this class was to allow somebody that maybe hasn't thought about these things since their last year in high school or maybe first year in college and has been in the lab making materials for 4 or 5 years to actually come to this subject. So I guess it's okay if it's a little bit of a review, and I'm only going to really hit the things that we need when we start working with qubits, okay? Okay, let's start at the very beginning again. So complex numbers. You probably remember from thinking about things like the quadratic formula, for example, that we encounter situations where we might need to take the square root of a negative number. And when we when we get to that situation, we realize that we need new numbers to answer that question. So when the square root of when our discriminant there is negative, we have to invoke the definition that I, this is an imaginary part of our complex number, is equal to the square root of -1. And so that gives us I squared equals 1. So if we have something like the square root of -16, that's just going to equal 4i. Or if we have I cubed, that's equal to -i. When people first considered taking square roots of negative numbers, they felt really uneasy about the situation, and they didn't think that these kind of imaginary numbers were going to have any utility. That's why they called them imaginary. But these complex numbers are a really important tool in all kinds of disciplines in science and engineering, from physics to electrical engineering, quantum information, applied math. So they often allow us to simplify equations or systems of equations down considerably. So that's kind of why we need to think about them when we're thinking about qubits. So there's two ways to express complex numbers. We can write them in rectangular form. So x equals I plus I, x equals, z equals x plus iy. Or we can express them in polar form, where we express x and y as a function of r and some angle. Here I have it written as theta. You might see it written as phi in other places. So x equals r cosine theta, y equals r sine theta. And so that gives us x plus iy equals r cosine theta plus ir sine theta. We can also re-express this polar form using Euler's formula in a really elegant way. So we can call r cosine theta plus I sine theta equivalent to r times e to the I theta. So Richard Feynman called this kind of expression for a complex number our joule, and he said it was the most remarkable formula in mathematics because it just beautifully simplifies problems for us. All right, so when we look at these complex numbers, here I have them written as a plus bi in the complex plane. They're uniquely determined by an angle in radians and a positive real number, r, which is defined as the absolute value of z. You can take the argument of a function, of the function that associates the angle with z, and this allows us to get the complex number expressed in terms of a phase, that's our angle, and a magnitude. And the reason to introduce this terminology is that the concept of the angle being related to the phase is really important in our quantum information. So we'll come back to that type of language down the road. All right, so if we look at this figure, our point here that's labeled A can be expressed or labeled many different ways. So we can label it in rectangular coordinates as 1 comma square root of 3. We can label it as equivalently 1 plus I times the square root of 3. We can use polar coordinates, and we can label it with r and theta. Here, r is 2 and theta is pi over 3. So we can label it that way. And equivalently, that allows us to write down 2 times cosine pi over 3 plus I sine pi over 3. And then we can use Euler's formula to get out the sort of r e to the I phi or theta terminology. So we can equate all of these forms. So we have this point in a polar or complex plane. So we have 1 plus I square root of 3 equals 2 times cosine pi over 3 plus I sine pi over 3. And that's equal to 2 e to the I pi over 3. So this gives us several ways to label that point. And depending on your situation, you might find one more convenient than the other. So the big thing that we have in complex numbers that we don't have in real numbers is an operation called conjugation. All right, so for a complex number, z equals a plus bi, the conjugate of z, which we usually call z bar, is a minus bi. So complex numbers always come in conjugate pairs. And so you can think of these conjugate pairs as symmetrically related to each other. So if we're plotting them in our complex plane here, you can see that they're related by just a mirror reflection about the x-axis. So we say that 2 plus 3i is the conjugate of 2 minus 3i, and 2 minus 3i is the conjugate of 2 plus 3i. In polar form, we can write these these conjugate pairs out as well. So the conjugate of z in polar coordinates is equal to r times cosine minus theta plus I sine minus theta, which is just equal to r times cosine theta minus I sine theta, which is equivalent to r times e to the minus I theta. Any complex number can be written in rectangular form, and if we wanted to add, subtract, and multiply complex numbers, they follow the same ordinary rules of algebra, and we just have to remember that I squared is minus 1. So it's easy to see that the conjugate of the sum of two complex numbers, I guess I'll write that here, is the sum of the conjugates of the numbers. So if I have two numbers, z1 equals to x1 plus I times y1, and z2 equals x2 plus I times y2, then the sum of the conjugates, z bar 1 plus z bar 2, is just the sum of the conjugates. The conjugate of the sum is just the sum of the conjugates. So we can rewrite this as x1 plus x2 minus I times y1 plus y2. And there's lots of other fun properties of conjugates. So if we have a complex number z equals a plus bi, the product of a complex number with its conjugate is a non-negative real number. So z times z bar is just a squared plus b squared. If z, our complex number, is 0, it can only be 0 if its conjugate is also 0. The real part of z and the real part of the conjugate of z is a. The imaginary part of z and negative, the imaginary part of the conjugate of z is negative b. And when the imaginary part of z is 0, z is real and conjugation doesn't do anything. So z is equal to z bar. All right, the last two little tidbits we need about complex numbers for thinking about qubits are the inverse and the absolute value. So the inverse, we can kind of use this little trick to figure out a convenient way to express the inverse of a complex number. Instead of just writing it as 1 over a plus bi, we can multiply the numerator and the denominator by the conjugate, and then kind of collect our variables and end up with this expression, which is a divided by a squared plus b squared minus b divided by a squared plus b squared times I. And the absolute value of a complex number, we just label it kind of the same way we normally label absolute values, is equal to the square root of the complex number times its conjugate. So for a complex number, a plus bi, that's just the square root of a squared plus b squared. And any complex number with an absolute value of 1, we call a unit. So problems in physics and quantum information are often going to be simplified by using one complex equation instead of 2 real equations. And what we've done so far, just by kind of reminding ourselves of what's going on with the math of complex numbers and conjugation, is to connect the square root of -1, the real numbers that are extended by that, and trigonometry. And those are all kind of keys that we're going to need to wrap our heads around what's going on with QISE. All right, let's talk about vector spaces. So there's a fun book called About Vectors by Banesh Hoffman. And in the beginning of the book, there's a fun quote that says, this book is written as much to disturb and annoy as it is to instruct. And I think linear algebra feels a little bit like that to many of us. But it is super duper handy, and it's absolutely necessary to understand quantum mechanics and quantum information. So linear algebra in general is just the study of vector spaces and linear operations on those vector spaces. And to dig into this subject, like I said, we really do need to understand how to work with them. And I think that a lot of the main obstacles to someone like me, at least as a synthetic chemist getting into this subject, is not understanding the postulates of quantum mechanics themselves, but the large body of linear algebra notation and ideas required to actually understand them. So that's the purpose of the next many slides, is just to get us on the same page with respect to working with vectors and matrices. So the basic objects in linear algebra are vector spaces. And a vector space that we're mostly interested in is Cn, so the complex space, the space of all n tuples of complex numbers. So that's Z1 all the way up to Zn. We can refer to this vector space using a column matrix notation. So we can just write it as Z1 to Zn. So we can also always represent a vector by an arrow. So that's kind of what's shown on the left here. And we usually label that vector with a bold-faced letter. So here the vector is labeled A to show you that it has both magnitude and direction. So the length of the arrow tells us that magnitude. The direction the vector is pointing, the arrow's pointing, tells us the direction. So we always have these two distinct methods of working with vectors. We can use a geometric description, so arrows, or we can use a set of numbers, components relative to some coordinate system. And when we saw the block sphere, the very first week of class, that was sort of the geometric representation of a qubit. And what we're going to see in the next few weeks are the matrix representations of qubits. All right, so just to remind ourselves about how we work with these vectors, they're pretty simple to work with. So if we want to, for example, add two vectors, so we have a vector u equals u1 plus, or u1 comma u2. And we have a vector v, which is equal to v1 comma v2. If we want to add u and v, then we just add the individual components. So that's equal to u1 plus v1 comma u2 plus v2. So very simple to do and very easy to represent in a Cartesian plane. All right, so when we're, one more thing that I want to mention about vectors when we're kind of thinking about them from a quantum lens. Because quantum mechanics is our main motivation for studying linear algebra, we're going to use the standard notation often that's used in quantum mechanics. So we're often going to label vectors like this with just a ket. Today I'm not going to kind of get us too far into bracket notation, but we will very soon. So just remember that when we're talking about quantum information and quantum mechanics, we'll represent vectors like this. And we've done that already, right? We've represented quantum states as ket 0 and ket 1. So those are vectors. All right, so there's two special vectors that we need to think about that are associated with the Cartesian coordinates. 1 comma 0 and 0 comma 1. So the vector that's associated with 1 comma 0 we call E1, and the vector that's associated with 0 comma 1 we call E2. And any vector associated with the coordinates a, b can be written as a sum of those unit vectors, E1 and E2. If the sum equals 0, then a and b must be 0 themselves, meaning that E1 and E2, these two vectors, are linearly independent. And the whole idea of Cartesian coordinates is that we're using these unit vectors, E1 and E2. And so if we mention a point in the Cartesian plane, A, B, what we really mean is the point corresponding to a vector, A times E1 plus B times E2. And we refer to the point AB, and we're assuming that we're using Cartesian coordinates when we do that. But we don't have to be using Cartesian coordinates, and often when we're dealing with qubits, we might need different bases to do our manipulations. So other pairs have this same linear independence property. For example, here I have H1, which I've expressed as square root of 2 over 2 times E1 plus square root of 2 over 2 times E2. And I have a vector H2, which is expressed as square root of 2 over 2 times E1 minus square root of 2 over 2 times E2. And here, H1 plus H2 is equal to the square root of 2 times E1. And H1 minus H2 is equal to the square root of 2 times E2. So if I have a new vector, 3 times E1 plus 0 times E2, I can rewrite that as 3 over square root of 2 times H1 plus H2 plus 0 over square root of 2 times H1 minus H2. And just rewriting that, collecting my terms, I can write that as 3 square root of 2 over 2 times H1 plus 3 square root of 2 over 2 times H2. So what this means is that a point with Cartesian coordinates (3, 0), it has the coordinates 3 square root of 2 over 2, comma, 3 square root of 2 over 2, when we're using the basis H1 and H2. And so we're going to do more on change of basis probably tomorrow. But this is kind of an important thing to wrap our heads around when we're starting to think about vectors and vector spaces, is that we don't always need to be operating in Cartesian coordinates. Coordinates are relative to the basis you're using. So there are times when a change of basis is going to make sense, and it's going to make the algebra and geometry less complicated and easier to understand, and so we'll do it. All right, so when we start doing math with vectors, it gets really complicated to keep track of everything, especially if we're going to be operating with higher dimensional spaces. So, for example, if I take this 5-component vector on the left, it starts getting really complicated to work with. And so instead, I can express that vector using a matrix. And so matrix is simply a display of a set of numbers. It doesn't have a numerical value itself. And this is kind of a general case for m rows and n columns. When the number of rows equals the number of columns, we call it a square matrix, and most of the matrices we're going to consider in quantum information are square because those correspond to linear transformations. All right, so vector notation. So if we have a vector V, we can express it as a matrix. We can express it either as a row matrix or a column matrix. And an important property of matrices is thinking about what's called the transpose. So the transpose of a matrix is the new matrix you get by reflecting the elements across the diagonal. So the transpose of the matrix on the left, A, B, C, D, is equal to A, C, B, D. So I've just reflected across the diagonal. Taking the transpose doesn't change any of the diagonal entries. Taking the transpose of a square diagonal matrix doesn't change the matrix at all. And the transpose of a row vector is a column vector and vice versa. So if I have a row vector and I want to take the transpose, I get a column vector. If I take a column vector and I want to take the transpose, I get a row vector. Why is this important? It's important because an n by n square matrix, we'll call the matrix A, it's symmetric if A is equal to its transpose. So for example, this matrix on the bottom here is a symmetric matrix because if I look across that diagonal, I have the same thing. The kind of colored boxes here show you another example of a symmetric matrix. Okay, so what about complex matrices? So I just said that in quantum information, we're going to be thinking a lot about numbers in the complex plane. And when the matrix has complex entries, we call it a complex matrix. The conjugate of a complex matrix is a new matrix formed by taking the conjugate of each of the entries. So if I have this matrix on the left, the conjugate of this matrix is just the matrix where all the entries I've taken the conjugate. So 0, 1 minus I, 3 plus 2I, 7 minus I, square root of 2 over 2 plus square root of 2 over 2I. All right, the adjoint of a complex matrix is its conjugate transpose and is denoted in our textbook as a dagger. Sometimes you'll see different notation used for the adjoint. So a dagger, that's going to be called the adjoint. And again, it's the conjugate transpose of our matrix A. In either order, you take the complex conjugate of the entries and transpose the matrix. An n by n square complex matrix A is called Hermitian if A is equal to its adjoint. So a Hermitian matrix is self-adjoint. So being Hermitian for a complex matrix is the same as being symmetric for a real matrix. So you'll hear all of these terms when we start getting into quantum information and quantum mechanics, like our matrices are Hermitian. This is what this means. So Hermitian is basically saying that the matrix is symmetric. Okay. Questions about this so far? Good. All right. What about determinants? So determinants are going to play a big role in how we think about manipulating our qubits. And so let's kind of remind ourselves what they are. So for a square matrix, we have a useful number called the determinant. And if I have a matrix here, A, then its determinant is AD minus BC. So I can think about this geometrically as well as just using the formula I just gave you. So if I consider a matrix A equals 2, 0, 2, 3, I can rewrite this as a product of two matrices, 1, 0, 1, 1, times 2, 0, 0, 3. And what this does is it stretches by 2 in the x direction. And by 3 in the y direction. And it applies a vertical shear. So I basically take x comma y to 2x comma 2x plus 3y. So that's shown in the diagram on the right. So I have my unit square here. And what I've done to the unit square by doing this is shown in the dotted line. So the parallelogram that I've kind of traced out is there. So the area of the parallelogram is its height times its width, and that's also equal to the determinant of A. So sometimes I think it's easy to rationalize what you're doing with a determinant by thinking about it with a geometric construction. But that's only really convenient when we're dealing with a 2x2 matrix. When we start dealing with higher order matrices, it's not really practical to visualize it in a Cartesian plane. All right, so if we want to take determinants in general, then we need to express our matrix in general. And we need a way to label all of the elements in our matrix. So, for example, we have this element A23, and that's an element in the second row and third column. And so we say that the element Aij is in the ith row and jth column. And as an abbreviation for the determinant of this matrix, we sometimes simply just write Aij. That is the determinant whose elements are Aij. And in this form, it looks exactly like the absolute value of the element Aij, and you'll have to tell from context with these meanings what's intended. So we've got to try to keep ourselves from getting confused. All right, so maybe I will stop here since I just downloaded a lot on you, and we'll look at how to do determinants in general starting at the beginning of next.